In the last class, I discussed the linear differential equation with constant coefficient and how can we represent it in the operator form. So here I am going to discuss about the procedure to solve the given linear differential equation with constant coefficient. And I told that the linear differential equation with constant coefficient may be two types. One is homogeneous and other one is non-homogeneous. So let f of d of y equal to fx, where so where I can say that f of x is 0 means it is homogeneous, f of x is non-zero means it is non-homogeneous. So now I am going to solve the homogeneous equation first. So right here, say one thing, type 1 for f of x equal to 0. Suppose f of x equal to 0. Then how can we find the solution of this one? So step 1, put, this is my equation 2, put d equal to m in equation 2. So wherever d is there in equation 2, you put m in equation 2. So if it is in the not in the form of d, you have to write it in the form of d, and you have to put d equal to m. Then what will happen? This will give you like this: f of m y equal to 0. Equal to 0. So if product of these two terms is 0, and here you know that y is the solution of the differential equation f dy equal to f of x, and so y is not equal to 0. Since y is not equal to 0, then we can say fm must be 0. So this equation is called auxiliary equation. This equation is called auxiliary equation, and in short form you can say AE. So what I am saying is, wherever D is there, I will put M and I will make it 0. So that equation is called auxiliary equation. So in the step 1, you have to find the auxiliary equation for the given differential equation. Then step 2. Step 2 is solve. Solve the auxiliary equation f of m equal to 0 and find the roots m. So if it is a second order, it is a second degree equation. Auxiliary equation is second degree. We can have two m's, m1, m2. If m is third degree, f of m is third degree, we will have three roots m1, m2, m3, and so on. So if f of m is nth degree, then we can have n root of the auxiliary equation. So after writing the auxiliary equation, we will solve the auxiliary equation to find the root of that auxiliary equation. Find the roots of the auxiliary equation. Then, after finding the root, how can we write the solution? How can we write the solution? So, step 3, write the solution. Write the solution. So, in depending upon the roots of m, we can have three cases. We can have three cases. Say, case A. Case is, suppose all the roots are real and distinct. Suppose all the roots of the auxiliary equation are real and distinct. Real and distinct. That is, say I have n roots and all are real and they are not repeated. All are different roots. All are different roots. And since I'm considering nth degree equation 1, so I will have n roots. And suppose all roots are real and they are different. Then how can I write the common solution? I can write, so in this case, the solution is called complementary function. So I can write the solution yx equal to c1 e to the power m1x plus c2 e to the power m2x plus so and so cn e to the power mn x. So what are your m1, m2, m3 and so on so mn? m1, m2, mn are the roots of the auxiliary equation f of m equal to 0. If you are getting three roots, m1, m2, m3 will be the three terms, three expressions. Okay, so depending upon the number of roots, you can have the solution of the given differential equation fd of y equal to 0. So if it is homogeneous differential equation, then this is the solution of the homogeneous differential equation. This is the solution of the homogeneous differential equation. Okay, and this solution is called complementary function. This solution is called complementary function. So in short form, you can say C dot F. A dot E means auxiliary function. C dot F means complementary function. So after solving the auxiliary equation, depending upon the roots, we can able to write the solution. And first case I said that if all roots are real and distinct, then we can have the solution in this form, which is nothing but the complementary function. And case B is, suppose the roots are real and some of the roots are repeated. Some of the roots are repeated. That is say m1 equal to m2 equal to m3, and thereafter none of the roots are same. M4 is not equal to m5 and so on, so not equal to say mn. Okay, so I have three roots which are same, m1, m2, m3, and then other roots are not equal. So in this case, how can we write the complementary function? So in this case, the complementary function is the solution yx. That will be whatever how many roots are repeating. For the suppose here I am having three roots which are same. So for that, what I will write, c1 first, then c2x plus c3 x square. Okay, so three roots are repeating, so c1, c2, c3, and I am multiplying every time x. So if it repeats two times, I will stop with c2, and if it is repeating three times, I will write c3 x square. If it repeats four times, I will go c1, c2x plus c3 x square plus c4 x cube, and then I can write any one of the roots, say m1, m2, or m3. So here I will write e to the power m3x because they are same, and then remaining thing will be, so up to c3 I have written here, c4 e to the power m4x plus c5 e to the power m5x and so on. So Cn e to the power mn x. So this will be the solution. This will be the solution if it is the case some of the roots are repeated and some of the roots are different and all of them are real roots. All of them are real roots. Then we can have the complementary function like this. For the repeated case, we can have c1 plus c2x plus c3x square e to the power m3x. Suppose I will have like this m1 equal to m2. Then what I will do here, I will write the complementary function yx equal to c1 plus c2x. I will not go for c3 because only two roots are equal. So c1 and c2x, and then I will write m2x. So this will be my complementary function if two roots are same, and all other the remaining roots are different means for the different root we can write like case 1. Then the third case is case C is if the roots are complex. If the roots are complex, that is the root m is nothing but alpha plus or minus I beta form. So here you see that alpha is the real part and beta is the imaginary part. So if you are getting somewhere root like this, then how can you write the complementary function? The complementary function will be nothing but e to the power alpha x. So whatever real part is there, you put that one as e to the power alpha x. Thereafter, you write it as c1 cos whatever beta you are having, you write beta x plus c2 sin whatever beta you are having here, you write beta x. So this will be your solution. This will be your solution if the roots of the auxiliary equations are complex. The roots of the auxiliary equations are complex. You can have the complementary function in this way.